Can it really lift that much? How can this tiny motor lift that much weight, or any weight for that matter? You can find that in this video. I always wondered how much weight can these little N20 motors can lift. Thanks to the gear system I designed for my trying to reach speed of sound video, now I can. In this system, when you spin the first gear, the last gear spins 241 times. But what happens when you spin the last gear? In this case, when you spin the last gear one time, the first gear spins 1.5 degrees. But what happens to the loss of this movement? It has to go somewhere, right? It becomes torque. Lots of torque. 1 Nm of torque in the last gear becomes 241 Nm of torque in the first one, allowing us to lift big things with this small motor. But before lifting anything, I have to tackle some issues. How will I mount the motor? How will it spin the gears? And which motor should I choose? There are many variations of N20 motors with different voltages and gearboxes. I can't buy and test them all, I need to find the right one. Also, how will I power the motor? I want it to run both ways, so I will need a motor controller. And finally, how will I attach the weights? I need to change this crank with a pulley somehow. One by one we'll solve all these problems. Let's start with finding the right motor. There is 3, 6 and 12 volt variations of the same motor. And I only have 12 volt power supplies, so I have to choose a 12 volt motor. But it shouldn't be a problem, because the 12 volt ones should be the most powerful ones. Let's calculate it to be sure. We'll need power formula for this. Power equals voltage times current. According to the datasheet, regardless of the voltage, the maximum current these motors can draw is 1 amp. Since the current is the same, if the voltage increases, so should the power. A 6 volt motor should use half the power of a 12 volt one. But how much power to be exact? A 6 volt motor at 1 amp will use 6 watts and a 12 volt one will use 12 watts of power. Most phones use more power than this when charging. There are even ones that charge at 120 watts. But which 12 volt motor should we use? There are many options with different speeds. These motors are sold with small gearboxes with different ratios. A higher RPM rating means lower ratio, and that also means lower torque. Here the ratio in our system comes into play. It has a ratio of 1 to 241. We'll use that to multiply the torque. But then what will happen to the speed? For example, if we spin the drive gear directly with a 100 RPM motor, how fast will the output gear will spin? This is quite simple to calculate. We just need to divide the speed of the motor with the gear ratio. 100 over 241 is 0.41 RPM, which means it will not even spin once in a minute. That's quite boring to watch at that point. Yes, you will get a high torque with a slow motor, but there's no point when the plastic gears can only handle so much. So reducing the torque and building something a little faster makes sense to me. Also, I have another way of increasing the torque. The drive gear and the motor doesn't have to spin 1 to 1. The motor can spin the drive gear with a smaller pinion gear, to get a ratio between them. And the total ratio would be this ratio multiplied by the rest of the system's ratio. What is the correct 12 volt motor for our system? Let's say the motor and the drive gear has 1 to 6 ratio between them. This would mean the total ratio is 6 times 241, which is 1446. That's an incredible ratio. And with that much reduction, if you use a slow spinning motor, we would grow old before seeing the weights getting lifted up. I want the output gear to spin at least once in 15 to 20 seconds. Let's calculate how many RPMs that is. Since there is 60 seconds in a minute, dividing that by 15 we get 4. If we use 20, that would be 3. Okay then, how fast does the motor need to spin for the output gear to spin at 3 RPMs? To find this, we again multiply the output RPM with the gear ratio. 3 times 1446 makes 4338. I'll need to choose the N20 motor with a speed around that, which won't be hard since there aren't many options around that speed. So I chose and bought the motor. This is a 12 volt 4000 RPM N20 motor. So how much weight can we lift up with it? Let's calculate it first, theoretically. But I want to give a disclaimer here. The motor I could find is a cheap no-name N20 motor, and it doesn't have a datasheet. I will use a datasheet I found for the same spec motor with a different brand, but I wouldn't be surprised if this one isn't as good as the branded one. According to the datasheet, the motor has a nominal load of 0.16 kg per centimeter at 3200 RPMs. That means it can lift up 0.16 kg, that's a centimeter away. This will be multiplied by 1446 thanks to the gear ratio, so the output torque will be 231 kg per centimeters. But how much weight can we lift up with this torque? First we need to find how far away the weight will be from the rotation axis. The steel rod has a radius of 4 mm and the rope has a radius of 1.5 mm. In total, this makes 5.5 mm. The torque value is in centimeters, so we need to convert it to millimeters by multiplying it with 10. We get around 2300 kg/mm. Now we can divide this by the distance we just found. Divided by 5.5 mm, we get 421 kg force. This is the weight we can lift theoretically. But let's not forget, we are disregarding a lot of important things like friction and the quality of the motor to get this number. Okay, since the motor is set, we need to find a way to couple this with the system. The simplest way to do it will be printing a gear that fits on the motor's shaft. But the last gear of the system is not a gear, it's a smooth disc, because it had to be aerodynamic for the last video. I don't want to print the last gear of the system since it's quite big. I have a simple solution that will print faster. I will print another disc for the motor shaft. These two discs will push and spin each other. I can hear you saying, isn't that gonna slip? The disc I will print will split in half and will have a slot for these elastic bands. These bands will hopefully create enough friction to eliminate the slippage. If you are not sure if these will work, you're not alone. According to our calculations, the disc needs to be 1/6 of the one in the system. Normally it's hard to remove small pieces like this from the printer, but in this case the screw holes came in clutch. Next, there is mounting the motor. The mount needs to push the motor into the disc, and the force that it pushes should be adjustable. I'm hoping to create enough friction between the discs this way. I have a couple design ideas for this. The motor can sit on a rail, and the force can be adjusted with tightening screws that pushes the motor into the disc. Another solution is making a linkage system that allows motion in one axis, like this, and pulling this linkage down with an elastic band to push the motor into the disc. I'll be designing the linkage one, starting with the side that will mount to the aluminum frame, then the part where the motor will mount to. If I get the tolerances correct, this should move freely after the print. To control the motor, I will use a simple motor driver and add some logic with an arduino. I will need to do the wiring and integrate them into the system. The motor and the motor driver uses 12 volts, but the arduino uses 5, so I will need 2 power rails. Luckily, the motor driver has a 5-volt regulator on board, which I can use to power the arduino. I'm thinking of an interface with 2 switches. One will turn on the motor and the other will switch its direction. This driver uses 2 pins to see how should it power the motor up. These are the pins I'm talking about. If 5 volt is applied to one pin and 0 to the other, the motor will spin full speed in one direction. If you switch the voltages, it will spin full speed in the other direction. If 2.5 volt is applied instead of 5, it will spin at half speed. I won't need to adjust the speed in the system, so I will always be applying 5 volts. You can use an Arduino to measure voltages at many pins between 5 volts and 0 volts. Also, it can apply different voltages to many pins at once. Thanks to this, we can use the Arduino to tell the driver how to control the motor. I'll be using 2 switches that are connected to 5 volts in one leg, and the other legs of the switches will be connected to the different pins of the Arduino. This way we can tell if the switch is open or closed by measuring the voltages at those pins. The first switch will control if the motor spins or not, and the other one will control which direction the motor will spin. Since our algorithm is ready, we can start wiring. First, I need to solder some wires to the 12 volt power connector. I also need to solder some wires to the motor, and finally I solder jumper ends to the switches. This film extractor I built in my last video helps a lot with the soldering. I have this terminal shield for the Arduino, and the driver also uses terminals, so I won't need to solder anything between these two. I am also designing a small tray to hold the electronics. Since there are many terminal connections, if the components are not fixed, the wires will come undone and drive me crazy instead of the motor. Everything is ready, we can start assembling now. I'm connecting the cables from the 12 volt input to the driver. I'm also adding jumpers to the ground and 5 volt output. Then I am fixing the driver and the Arduino shield to the tray. Now I will use the jumpers I inserted earlier to connect the ground and the 5 volt to the Arduino. I'll check the voltages before inserting the Arduino, no need to fry it. Next there are switches. I'm attaching them to their places. Connecting their jumpers to the Arduino pins I set up in the code. Let's give it a try. It works. I can also change the direction. Time to fix the motor in place. It bows like this. It sure isn't a high quality motor, but it is respectful, I guess. Fixing the motor mount to the frame now. There it is. Let's power it. To attach the weights, I'll be tying a rope to these rod holders I used to fix the crank to the rod in the other video. This time there will be no problem with slipping, since the friction will be really high after some turns on the rod. This was the fastest motor I could find, but even with it, the rod turns really slowly. Let's start light with just 2.5 kilograms. Hi, John from Future here. Thanks to trying to reach the speed of sound video, the channel memberships are now open. And if you want to support me to reach the speed of sound next time, you can click the button below and join the channel. When you actually click the button, a video will start to play. Please watch it all the way through, because I have some concerns about YouTube's membership program and I mentioned them in that video. Future John out. It should be easy for the system, but if we encounter any problems, it's easier to solve it with this weight. I know this is not the most efficient motor mount, but I'm really enjoying this little guy jumping around. Let's try 7.5 kilograms next. It is really slow and quite loud, but no problems so far. And lift off, 7.5 kilograms, done. Let's try 10. The sound of the motor is worse now, but it is like this even when it's not under any load. The fact that it's low quality really started to show now. Even when I got it brand new, the gearbox was slipping a bit, but not this much. It is louder due to the gears slipping and grinding. And the motor itself isn't even sweating yet, it's cool to the touch, it's just the small gearbox that it came with causing problems. The weights are almost up. And again, lift off, not bad. You can feel how ridiculous this ratio is when I raise the motor and let the weights fall down. I can stop them with just a touch. That's the reason why the friction from the elastic band is enough. Let's try 15 kilos. That's all the weight I got at home. If it can lift this too, I'll need to buy water jacks or something. It's not a bad start. Hi, it's Can from Future, again, and it's now the holiday season, so Merry Christmas or Merry the holiday you are celebrating. And did you know the Santa Claus is actually from here in Turkey, according to many historians? If you didn't, now you know. See ya! I think this is the point where things start to go south. The motor is spinning, but the gearbox is so worn down that it just slips. I can push and move the gears to make them touch, and it starts spinning. But I believe these are its final moments. It is still strong enough to tip the table over, that's something. I weight down the table with this bucket, should be more than enough. The motor is grinding again. No, it slips too much. Just to be clear, the 3D printed gears are fine, but the built-in gearbox of the motor is not fine. It is still going strong though. And lift off, again, that's impressive. The motor is done for real now. It spins, but the gearbox is completely shut. It is completely useless now. The shaft spins freely. It's not connected to the motor anymore. It did lift all the weights at home. When you realize the motor is just 9.5 grams, it is lifting more than 1500 times its own weight. I wonder if I had a high quality N20, would it be able to get close to the theoretical limit? Let me know if you want me to try that, or I can put a bigger 540 size motor to break some gears. Like and subscribe for more. See you in the next project.